Thank you. Perfect. Okay, so my name is Zoltan Sternovsky. Waiting for the slides. The title in the printout somehow is shorter than it really intends to be. Anyway, I can recognize my co-authors. Evan Thomas is sitting in the audience. He has I believe, number 36 is his poster on a similar topic. Actually, he's doing most of the work I'm going to present. And what I'm really want to show you is preliminary results from our new experimental facility in Boulder. We are interested in dust research throughout the solar system and beyond, and including micrometeoroids coming into the Earth. There it is. Okay. Experimental investigation of micrometeoroids, ablation using a dust accelerator, and preliminary results. These are my co-authors, Evan Thomas. Okay, so what is the motivation really for this work? Dust research, dust environment in our solar system. So if you look at you can fly dust instruments in space, and it has been done, and you can measure the micron and submicron size particles very accurately with good precision, with good instruments. However, if you look at the mass influx as a function of dust size, you see that actually most of the dust either comes as very large boulders, occasionally once in 1,000 or hundreds of years, but there's a big strong peak around 100 micron size particles. These particles cannot be measured with simple instruments on spacecraft because their flux of these particles is not sufficient. On the other hand, they turn into a visible stream as they enter the atmosphere, and this peak is a little bit outside of the visual matters. On the other hand, it is right in the middle of the sensitivity of meteor radars. So meteor radars would be the right way to constrain how much dust is coming in. And here I show a picture of the velocity distribution as measured by high power large aperture radars. And you see that this radar, this is the Arecibo radar, is reporting this distribution with particles in the 20, 40, 60 kilometer per second range. And this, unfortunately, is inconsistent with models. So, for example, there is a dust model that's based on the shape and characteristics of the zodiacal cloud. And that would tell you that most of the dust particles falling into the Earth essentially falling with the escape velocity, so close to 10, 15 kilometers per second. And the question arises whether are the radars actually sensitive to these particles? Is it possible that these particles exist, they fall in with low speed, but because of low speed, they don't generate a big enough ablation signal, and the radars miss it? So there's plenty of unknowns, actually. One of them is the total mass input into the atmosphere that ranges from 5 to 200 tons per day, roughly. The radars predict on the lower end. The velocity distribution, we don't know if how strong is the bias that radars introduce into this measurement. And if we solve those, then we can learn something about the origin and the composition of the particles that are coming in. So let me show you a few equations about the ablation. It's a relatively simple set of equations. So the particle, as it enters the atmosphere, is going to slow down. The slowing down is proportional to the velocity squared. So that's the momentum equation. The second one is the energy conservation equation. So the energy that's put in the frictional heating of the meteorite is proportional to velocity to the third power. And that goes into black body radiation, heating of the particle, and eventually, if it heats up enough, it goes into the ablation or the evaporation of the particle, the mass loss. And the mass loss is simply an evaporation depending on the partial pressure of the particular compound. And how you turn this into a signal measurable by radars is that you take the material comes off in form of ablated atoms. And these ablated atoms move with the same velocity as the particle, as the meteorite, and will slam into molecules of the atmosphere. And there is some conversion fraction, the ionization efficiency, which is a strong function of velocity. What is the probability that an atom, a collision, is going to produce a ion-electron pair? Turns out that all of the measurements, relevant measurements, have been done in the 60s and 70s. And there are two different sets of experimental setups. One, which is applicable only to alkali metals, uses you generate an ion beam from the alkali metals, and then you run it through a charge exchange collision chamber. You turn them back to neutrals, and then you measure the cross section. The second one is to use a dust accelerator. So if you shoot a dust particle with a high enough speed into a compartment in the system with a high enough pressure, then you will completely ablate this particle, and you can measure the ionization efficiency. So this was limited. There are limitations, velocity limitations, number of materials studied limitations, and of course this seems to be a little bit outdated. A little more details on the dust accelerator, because this is what we want to reproduce and improve upon. So the particle comes in here, it ablates, and if it ablates completely, then you know what is the mass, you know how many atoms collided with the background gas, and you can calculate what is the ionization probability as a function of velocity. So this has been measured between about 20 kilometers or so. Okay, so there is a theoretical or an assumption of shape or function for the beta function. It depends on a fitting parameter and also V0. V0 is the minimum ionization speed. It depends on the ionization energy needed. And you can fill up, of course, this figure from all the way from V0 to high velocities. But as you can tell, that even for the materials that we know, sodium, potassium, and iron, this is the experimental data really doesn't provide a strong constraint on either on the shape of this function or how it behaves at low velocities. And low velocity is what we are really after, because that's where we can decide on the meteor radar performance or sensitivity. Okay, so this is our dust accelerator, a different view. That's the high voltage generator, 3 megavolts is generated there. That's the dust beam, the beam line, and the particles eventually end up in this ablation. And this is our experimental chamber, about 2 cubic meters in volume. And the next figure shows you the updated mass versus velocity, what we can achieve, what we can produce in this facility. We have filled up, if you have seen this earlier, we have really filled up this space, so we can generate micron-sized particles, a couple of microns at lower velocities, or higher velocity particles in the submicron range, and we now have 50, 60, 70, all the way up to 100 kilometers per second particles. Okay, so this is the picture of the ablation facility itself. This is the gas cell. Which is filled up with about half a torr of gas, and of course it's connected to a high vacuum beam line. So we need a differential pumping system in between. And what really is inside is this. So the particle in here is coming from the left. The particle is charged. That's how it's accelerated by electrostatic forces. It flies through a pickup tube detector. Here we measure the velocity and the charge of the particle simply by the timing and the amplitude of the signal, from where I can calculate the mass. So we know the mass and the velocity of the incoming particle. Then we have the differential pumping system, and then we have the ablation chamber with the pressure in that range roughly. It's about 50 centimeters long, so about that long. And the particle shoots in, eventually heats up and starts ablating. And our improvement is that we installed a set of, or a pair of segmented and biased charge collectors. So what we want to measure is the charge that's generated by the ablation. We separate the positive and negative charges and collect both ends. And so this is a sample data set. So those are the points are the charges collected on each of the detectors as a function of range as you propagate through. Okay, so we by we I mean Evan went ahead and completed this set of measurements. So went down to all the way close to 10 kilometers per second and told me what is the beta value. And we were ready, or publish or write the manuscript. And then we realized that there's a problem at low velocities, and that's what I would like to illustrate here in the next couple of pictures. So this is the collected charge on those charge collecting electrodes as a function of distance from the entrance point. This is for a 10.4 kilometer per second particle, happened to be 70 nanometer in radius. And as you see, what happens is that the particle comes in, it's not hot enough yet to ablate, and it heats up, and then and it starts losing mass. The mass loss is producing ionization, and then before the particle exits the ablation segment, the signal goes down to 0. And we said that's great because the particle completely ablated, or almost completely ablated. We can simply calculate beta by taking the total amount of atoms in the particle and divide it by the total charge that you have collected. And then we realized that that's actually not the case. So we used the ablation model and calculated the velocity, temperature, mass, and the solid fraction of this particle, estimated, I should say. So we start with 10.4 kilometers per second, but the particle does decelerate a little bit, and we realize that this particle actually doesn't ablate completely. And the reason is because you are in the 10 to 9 kilometer per second range. This is where beta is really changing very strongly. So this strong decrease here is not because the particle is disappearing, it's because it's slowing down a little bit, and that makes a big difference in the ionization efficiency. Okay, so we figured that out. Now I know that the particle is losing less mass, so compared to that, I have to adjust the beta value, and the beta value is going to get bigger. I cannot tell you right now just yet how much, if it's going to be a factor of 2 or a factor of 10, because we need to run a bigger set of data and find good fitting parameters, not just on a single particle. I have a faster particle. This one is 18.6 kilometers per second. This one for sure is completely ablates. So those are reliably measured. You can measure the beta value. The little hiccup here is that we're not able to reproduce exactly the shape of this ablation curve. The experimental, the model actually produces or predicts the ablation happening a little earlier than what we measure. And so that's the data point right there. So essentially the summary and conclusion. So there is a need for these kinds of measurements, and particularly extending this to lower velocities. We have a new ablation facility now operating at CU, which is open to collaboration. I would like to advertise that. We have good quality measurements, not only for iron, so please visit Evan's poster, for velocities larger than kilometers per second, which are reliable. And then the next step is really take a careful look at the analysis at lower velocities. Thank you.
All right. Well, let's keep going so that we can get to lunch. So the last speaker in our session is Jamie Zalay, and the title of the talk is